The dimension of the subspace spanned by the real vectors yada 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 is 2, 3, 4, 5, or 6. Okay, so the answer is certainly not 5 or 6 because they are vectors with 4 coordinates. And I can see immediately some of them, there's clearly linear dependence between, like an obvious linear dependence between some of these specific ones. The first two are just multiples of each other. The last one is all zeros, so we can throw some of these out right away. What I'll do is I'll write down, let me reduce the, oh, and the third coordinate in all of them is 0. So, oh, but that, yeah, okay. So let me kind of throw these out one at a time with specific reasons for why I'm able to do that. Okay, so we're looking for the span of these. We're given 6 vectors. We're looking for the span of them. And so I can throw out vectors that are linearly dependent with the rest of the set. So this one, immediately we can throw that out. We don't care about it. The second one is exactly twice the first one, so we don't care about that one either. We can throw that out. So I want to see if I can figure out just very quickly in my head how to construct some of these as linear combinations of the others. The answer is certainly, the maximum is certainly 3. It's just a question of whether the dimension of the span could be 2. I know the maximum is 3 is because, like I said, all of these coordinates are 0. So which of these can I throw out? I can throw out, what I'm going to do is I'm going to show, just sort of a little bit of hand waving and sketching here, how I believe I can simply construct this one from the others. So, wait a minute, what do I want to say here? I can construct this one from the 3 others. So I'm not going to write out the details, I'm just going to kind of speak out loud what I'm thinking here. I can multiply this one by a real number such that the fourth coordinate is the same. Clearly, if I multiply this by 8 over 3, then the fourth coordinate will be that. Then from there, I will have something in the first coordinate. I can add some linear combination of this such that the first coordinate of my resulting thing is a 1. And then whatever the result is, I can add some linear combination of that to make the second coordinate a -2. So I can write this vector as a linear combination of those 3, so I can get rid of it. And now, it's kind of just obvious to me that these 3 vectors are linearly independent. I definitely, like, this is the only one that gives us any non-zero coordinate in the, or any non-zero value in the fourth coordinate. And I can't, yeah, these two on their own will never add up to something 0. So these 3 vectors, they're linearly independent, and so their span is going to be 3, which is the number of vectors. So if I call this thing, what should I call this? I don't know. I'll just call this A, this collection of vectors. then the dimension of the span of A will be equal to 3, which is one of the options we're given. So pretty confident in this one. You know, the couple things that went on here. You can immediately rule out 5 and 6 because even though we're given 6 vectors, they only have 4 coordinates. So the maximum dimension of the span is going to be 4. I see some of the vectors are redundant, so you can throw those out immediately. And then once I was reduced down to only 4 of the vectors, this one, these 2, and this one, I can kind of just see the sequence of computations in my head that I would need to write this one as a linear combination of the other 3. Anytime you're kind of trying to do something like that, you know, having 2 vectors that share non-zero coordinates, but there's 0 everywhere else, that kind of gives you a head start. And then having a vector that has zeros in all coordinates except for one of them makes it very easy to kind of finish the last step in constructing this vector. Yeah, not much more to this one, but if I think of anything more to say, I'll write it down in the description. Thanks for watching.